Good evening, I'm Gio Almonte and today we'll be discussing some problems from chapter 24. For first question, we have a capacitor is made of two hollow coaxial iron cylinders, one inside the other. The inner cylinder is negatively charged and the outer is positively charged. The magnitude of the charge in each is 17.5 pictocoulombs. The inner cylinder has a radius of 0.45 millimeters, while the outer one has a radius of 6.2 millimeters, and the length of each cylinder is 21 centimeters. A. What is the capacitance? And B. What applied potential difference is necessary to produce these charges on the cylinders? So, first let's look into our given. So for our charge, we have 17.5 times 10 to the negative 12 coulombs. Coulombs are also known as 17.5 picocoulombs. For our length, we have 0.21 meters. This is just our 21 centimeters divided by 100, and we end up at 0.21 meters. For our first radius, our inner radius, we have 0.45 times 10 to the negative 3 meters. So what we did is, since it's millimeters to meters, we just divided everything by 1000 or multiplied it by 10 raised to negative 3. And our second radius is 6.2 times 10 to the negative 3 meters, or we just multiplied 6.2 times 10 to the negative 3. So what is the formula for capacitance? Well, the formula for capacitance is 2 pi E naught L divided by the natural logarithm of RB over RA. 2 pi is, as you know, pi. E naught is equal to 8.85 times 10 to the negative 12th. L is the length of each cylinder, and RB and RA are the respective radiuses of these cylinders. And as we know, we're going to find for the potential difference later, and potential difference is just equal to the charge over the capacitance. Okay, so first let's input our equation for our capacitance. So 2 pi times 8.85 times 10 to the negative 12 multiplied to 0.21 divided by ln 6.2 times 10 to the negative 3 divided by 0.45 times 10 to the negative 3. After solving this, we end up with an answer of the capacitance is equal to 4.45 times 10 to the negative 12 V. Next, for our potential difference, as we know, potential difference is equal to Q over C, or charge over capacitance. So all we need to do is to input our equation. So we have the potential difference is equal to 17.5 times 10 to the negative 12 divided by 4.45 times 10 to the negative 12. And finally, we have an applied potential difference of 3. For our next question, we have a question. For the system capacitor shown in this figure, a potential difference of 25 V is maintained across AB. What is the equivalent capacitance of the system between A and B? How much charge is stored by the system? How much charge is a 6.5 NF capacitor store? And what is the potential difference across a 7.5 NF capacitor? So we must remember first that for a series circuit, the capacitance is equal to 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So basically, it is just the 1 over the reciprocal is equal to the 1 over the reciprocals of the individual charges. For a parallel circuit, the capacitance is just equal to the summation of all the individual capacitances, or C is equal to C1 plus C2 plus C3 and so forth. So first, let us look into the capacitance between A and B. So based on the figure, we can see that this is a straight line and there are no forks in the circuit. So we can already predict that this is a series circuit. So we'll be using the first equation. So to get the total capacitance, all we need to do is to get the inverse of the summation of the reciprocals of the individual charges. So we'll get 1 over 18 plus 1 over 30 plus 1 over 10 raised to negative 1. So for the capacitance to A to B, we end up with an answer of 5.25 NF. Meanwhile, since we're trying to find the total charge stored by a system, first we need to find the total capacitance of this entire system. So as we know, we can treat this series total capacitance of the series as let's say as a more of a parallel charge already. So what we can do is we can just add this to the remaining charges. So we'll take our charge of 5.29 plus 7.5 plus 6.5, and we have a total capacitance for the system as 19.29 NF. Next, for part B, as we know, to find for the charge stored by a system, Q is just equal to C over V. This is derived by the previous equation in our first question, where we found out that V is equal to Q over C. So it's just simply Q is equal to 19.29 NF, which is what we solved a while ago, multiplied to the given, which is 25V, and we end up with a charge of Q is equal to 482.25 nanocoulombs. For letter C, we do the same thing. So since we're already given what our capacitance is, we have Q is equal to 6.5 NF multiplied to 25V, and we end up with a charge of 162.5 NF. Now, what is the potential difference across the 7.5 NF capacitor? Well, as we know, if the circuits are parallel, that means that no matter what kind of capacitance they have, the potential difference is the same. So since we know that we already have a potential difference of 25 is maintained across AB, we can also infer that the potential difference of a 7.5 NF capacitor is also 25V. For our next question, we have a question. The potential difference of VAB is equal to 48V is applied across a capacitor network if C1 is equal to C2 is equal to 4UF and C4 is equal to 8UF. What must be the capacitance of C3 if the network is to store 2.9 times 10 to the negative 3 joules of electrical energy? So let's look at our given. So C1 is equal to 4UF, C4 is equal to 8UF, C2 is equal to 4UF, and C3 is what is missing. Meanwhile, we have our potential difference, which is equal to 48V, and our total electric energy, which is 2.9 times 10 to the negative 3 joules. So first, to find the individual capacitances of each section, we first need to find the total capacitance. So to solve for total capacitance, let's look into first the formula of solving for electrical energy. So U is equal to 1/2 CV squared. And after this, we can derive CT, which is the total capacitance, by CT is equal to 2U over V squared. So U represents again the total electric energy, while V represents the potential difference. So all we need to do is to input our numbers. So C is equal to 2 times 2.9 times 10 to the negative 3 divided by our potential difference squared, which is 48 squared. After solving, we have a total capacitance of 2.52 times 10 to the negative 6F. Let us first divide our capacitances into different types. So first, let us define our terms. So let us call the C slash is equal to the summation of the capacitance of the upper part of this circuit, which is the ones that include C1, C2, C3. As we can see, C1 and C2 are a series type of circuit, while when in combination with C3, it becomes a sort of a parallel type of circuit. That's why this overall C0 is equal to C12 plus C3, because it will end up looking like a parallel. But first, we need to solve for C12. So since when we look at it, it looks like a series, we know that 1 over C12 is equal to 1 over C1 plus 1 over C2. So once we input it, we find 1 over C12 is equal to 1/2. After raising everything to negative 1, we find that C12 is equal to 2UF. Next, we need to find for C4. So what we do is we find that 1 over CT is equal to 1 over C4 plus 1 over C0, because as you can see, the C0 and C4 form some sort of some sort of series circuit, because as you can see, there's no more break along the circuit. So we have to use reciprocal. So after this, what we need to do is we just need to simply derive C0. So 1 over C0 is equal to 1 over CT minus 1 over C4. So as we saw a while ago, we got our 1 over CT is equal to 2.52 UF. So we can just use 2.52 since everything here is UF, and we can just cancel out the UF. So 1 over C0 is equal to 1 over 2.52 minus 1 over 8, with 1 over 8 representing C4. So 1 over C0 is equal to 1 over CT, which is C total, minus 1 over C4. So we find that 1 over C0 is equal to 137 over 504. So since these are still under a numerator of 1, we can raise everything to negative 1, and we find that C0 is equal to 3.68 UF. So we just put back the UF from a while ago. Next, all we need to do is to input our equations. Since we want to find for C3, we can just move the elements in the first equation we got, which is C naught is equal to C12 plus C3, and exchange it until we get C3. So C3 is basically C naught minus C12. So we have C naught, which is 3.68 UF, minus C12, which we already solved as 2 UF. Finally, we have a C3 of 1.68 UF. So this is the final question for chapter 24, and I hope to see you guys again in our next chapters. So I hope you understand. Thank you.